Just to finish off today's lecture, section 14.4, we still need to talk about increments and differentials. So an increment, that would be, whoops, that would be change in y. And you can see on the graph here that I wrote what change in y is. I have labeled here a and a plus delta x. Delta y is the change in y value of the function. Okay. Now, this is an increment. A differential in other words, is dy. dy and dx are called differentials. So dy measures something slightly different. So if I put a tangent, let me get a slightly more contrasting color. Whoops, maybe red. If I put a tangent line at A, and I missed the mark a little bit, let me try one more time. There we go. So if I put, this is a tangent to f at x equals a, what dy represents is the change in the tangent. And so dy is this distance here. Now, we use differentials to calculate error. But before I do that, let me just say one more thing here. So or change in y over change in x is the slope of the curve. Average. And dy dx is the slope of the tangent. Okay, so generally, differentials are infinitesimal. Which just means really small or approaching zero. And we usually use the change in x and change in y to show like bigger values in practical applications. The total differential let's just look at an example. If I have z equals f of xy, then the total differential is dz equals fx dx plus fy dy. So the total differential is the sum of the partial derivatives times the differentials. And you can use this to calculate error. So for example, dx is going to be the error in the x direction. Okay, So let's just take a look at a quick example of how you would use differentials to calculate error. You may have seen this in physics before. So if you're finding the total error in the measurement of the volume of a cone, I'll say in calculating the volume of a cone. So we start with the formula for volume. For a cone, that is 1/3 pi r squared h. Notice volume is in terms of radius and height. So those are our two independent variables. The total error in volume is going to be dV. And that is going to be equal to the derivative of v with respect to r dr plus the derivative of v with respect to h dh. So we get dV equals, now if I take the derivative of this with respect to r, I get 2/3, whoops, 2/3 pi r dr. And then when I take the derivative of v with respect to, the partial derivative of v with respect to h, I just get 1/3 pi r squared dh. Now, r would be the measure of the radius. H, similarly, measure of the height of the cone. dr is error in radius. So, like plus or minus 0.1 centimeter, etc. And similarly, dh is the error in the height. So let's do a quick example of finding the maximum error in calculated the volume of a box. And the box is going to be, let's see, 60 by 80 by 50 centimeters. And the error in each dimension is going to be 0.2 of a centimeter. Oops. 0.2 centimeters, so 2 millimeters. So that just means that whatever you're using to measure the box's dimensions has an error of 0.2 of a centimeter. And so therefore, what we're going to start with is the volume of the box. The formula for volume of a rectangular solid, length times width times height. Here's a picture of our box. Oops. So we'll say that my My box is sadly not to scale even a little bit, but pretend with me, if you will. We'll call this the 80 and we'll call this the 60. Obviously the 60 looks double the 50, so it's not to scale, but okay. So we start with the volume and then we find the total differential. dV is going to equal to, if I take the derivative with respect to L, I get WH dl plus LW dH plus LH dl. And for each of these dl, dh, whoops, I think that last one needed to be dw, so let me fix that. So those are all 0.2. And we can arbitrarily assign the length and the width and the height to 50, 60, and 80. So the total error in calculating the volume is going to be 60 times 50 times 0.2 plus 50 times 80 times 0.2 plus 60 times 80 times 0.2. Let me put parentheses. And let me double check and make sure I did all the right combinations. Yes, I did. So the total error is 2,360. It's volume, so it's cubic centimeters. Now, this might seem like a huge error, but you have to remember that volume tends to be really, really big numbers. So the actual volume, or the calculated volume, would then is coming from 50 times 60 times 80. So that's, let's see, 5 times 6 is 30. So 3 times 8 is 24. The 0 from the 30, and then 3 more zeros. The volume of the box is actually 240,000 cubic centimeters. And so our percent error is really just 2360 over 240,000 times 100, which comes out to be about 1%. Okay, so even though it seems like a large number, relatively small number compared to the actual volume of the box. That's it for section 14.4. I'll go ahead and leave it at that for the moment.